Hi, my name is Jasmin Krosinger. I'm with Graz University of Technology, and I'm happy to present to you today a little sneak peek on RF design for ultra-low power wireless communication systems. So in particular, the talk focuses on RF design for sustainability. With ultra-low power wireless communication systems, we can solve sustainability issues related to the Internet of Things. And you can see here one picture, one schematic, where I show to you what is actually the vision behind the Internet of Things. A lot of devices in our daily lives or in our professional lives are connected then wirelessly to the Internet. And one estimate of these devices, the number of devices per square kilometer, is that there will be 10 to the power of 7 devices. And this is, as you can see, a massive deployment of wireless nodes that we'll have to expect with reaching a full digitalization, which creates a lot of troubles when we think of sustainability on environmental, but also on economic levels. You will have with every of each device a product object, you will have a wireless device, a wireless sensor to connect the object to the internet. And this wireless device might then need to use a battery. So with some radio frequency designs, and in particular ultra low power designs, we are able to solve sustainability issues that come with the Internet of Things. We radio frequency engineers can actually solve sustainability issues on environmental level and economic level related to the Internet of Things. We can realize radio frequency designs that allow us to only consume ultra low power for communication. We can provide power wirelessly towards these devices so that we can get rid of the batteries at all, because batteries are toxic and getting rid of them will increase the sustainability of the devices. And also, if we are not able to operate without a battery because we want to monitor something 24/7, then at least we can extend with this ultra low power consumption, we can extend the battery life from 2 to 10 years. Another aspect that we radio frequency engineers can provide is we can help reduce the footprint of the devices and also help with our RF designs to allow a high level of integration to reduce the production costs as well as the end of life costs. If you think of using CMOS and then bringing, for example, the antenna of this wireless device down to the size of the CMOS chip, so that we use less rare material, less copper material to create such an antenna. In this little teaser video, I'll talk about devices like this. This is a device that we at the university realized together with Infineon Technologies that are also based here in the Graz region. And it's a battery-less sensor device, actually the first of its kind. We use a specific communication technology here in particular so that we can really ultra low power wireless communication at hand so that we don't need any battery at the device side. And to provide, however, the power, what we'll do is we use power transfer, wireless power transfer from a reader device, an interrogator device. And the technology that provides us with these possibilities is called radio frequency identification, and in particular, high frequency RFID, where we operate at 13.56 megahertz. That's the same interface that we also use for contactless payment using our phone. So RFID is a technology that can provide battery-less operation of devices because we provide them power towards such a device with a reader, interrogator. And on the device side, the modulation type that we use, so-called load modulation, is very power efficient. And so the communication and is easy to establish. And the read range, however, in this case for 13.56 megahertz is kind of reduced because the means how we communicate here and transfer power is using magnetic resonant coupling. So we're operating in the near field of the device. That is why you can see here a coil on the package. This thing is actually fully highly integrated. We use here a packaging technology on wafer level that is provided by Infineon, and it's based on a CMOS technology. And we use a system in package concept where we put the antenna, in this case a coil, on the package. There is, of course, also possibility to use concepts like system on chip, but we'll speak about this in a minute. So here, if you take a look at RFID tags and what are out there, you'll definitely see these tags used in identification, but also more and more in sensing. So they have a sensor interface, a full-fledged sensor on the device, as you've seen before on this example that I showed you that we created together with Infineon. But if we take a look at the size of these things, of these transponders, tags as we call them, you can see here now these conventional size tags. Here, this similar, like the same as a payment card. You have here an HF RFID chip, this time provided by NXP, and then you have a coil that is designed in a way so that the device is magnetically resonant at 13.56 megahertz. And the size is usually 8 times 4 centimeters, so really credit card size. But that's typical card size that we'll see here. And it's not as densely integrated as we would like to see it. In particular, if you think of this coil that you can see here, it can be up to, let me think, 2.8 meters, which is crazy. It's a lot of copper that we're using here. And I'll show you today a solution that gets rid of the copper for this coil, which is quite cool. Now, taking a look at these conventional size tags, you can see that the coil that we use, or the antenna, in the case of UHF RFID, is definitely, characterizing the size of the transponder. So as already said before, so what we can do is to make the sizes of these devices smaller, is we can use system in package paste methods. So bringing the coil on the package. This is the device that I showed you before, a full-fledged sensor device, operated batteryless and power provided wirelessly to it by an interrogator or a reader. Kind of, it could be the phone. This is another the product actually that is out there provided by Infineon. It's called a coil-on module, and you can see it here. And this coil-on module is a product. If you have a chip, if you have a payment card, and you have a chip provided by Infineon, then definitely it is a coil-on module, because this is what they do. They have here, this is the top side. So if you look at your payment card, these are the contacts that you use for contactless payment. You have the payment terminal, you insert your card, here are the contacts. And on the other side, what you have for contactless payment, wireless payment, is you have the coil on the package, as you can see it here. And this little guy here is the payment chip. And so embedded in your credit size card substrate, its size as a credit card, you have then this coil-on module, and then adding on to this so-called booster antenna, so that you have a read range of about 10 centimeters that you would like to have for payment. this is what the standard is saying. So it's following the proximity standard of HF RFID technologies. Well, we have communication ranges of up to 10 centimeter. Why they use this extra booster antenna is because this standalone coil module would not reach this range of 10 centimeter because we're still operating at 13.56 megahertz. And if you put the coil on a smaller size, you only have a reduced size of area where you can couple the magnetic field. And of course, you have less power transfer and less power available for communication. And so the distance of communication, we call it read range, is reduced considerably. So as such a standalone device, as you can see it here with the sensor and here for payment, can actually achieve only a read range of up to 1 centimeter. But we'll see it later on. There are new developments, and that's quite exciting to see. So if you want to even miniaturize the devices considerably more, you use system on chip based concepts. So you can integrate the coil on the top metal layers of your CMOS device. You can see here 4 different realizations that we created together with Infineon. And it's, for example, a dual band transponder where we can operate at HF 13.56 megahertz and UHF 868 megahertz. In this case, the area sizes are 1 square millimeter. So it's very small. The coil just covers this 1 square millimeter, as you can see here, this outer rim. In the end, with this small coil still operating at the same frequency, you again have to deal with a read range reduction. It is what it is. We cannot beat physics. So we have read ranges for these little guys here in the millimeter range, if we're lucky. Using this capacitive coupled chip here, or tag here, we are even in the micrometer range. But that's a different story. Today, what I want to just show you is quickly the coil-on system design, and then this new advancement that was just recently announced by Infineon on a new coil-on module design. Miniaturizing transponders started actually back in the 2000s with the French Telecom, and they really suggested for the first time, so let's put the coil on the chip. It's way smaller. It might have so this is really it's really good for some applications. And so it took a while, however, after having the first idea, to show successful wireless measurements. Let's call it contactless measurements. It took until Shameli et al. At the Broadcom Corporation in California in 2007, when they really showed at 900 megahertz, so at UHF frequencies, and contactless successful wireless measurement with a coil on chip. And it took another 4 years when at the Nagoya University, Kim et al. Finally showed a successful coil on chip wireless measurement at 13.56 megahertz. And this is what you can see throughout history. First, if you miniaturize, you're always successful at higher frequencies first. Then if you go down frequencies, you really have to fine-tune your design because it's getting harder and harder with the growing wavelength that you have to deal with. The first coil-on modules, the one that is now an Infineon product, were actually presented also back in Japan in 2011. A coil-on module, as you can see it here, announced by Hitachi Chemicals, or then at 13.56 megahertz by Murato Manufacturing. But I want to show you now a bit more details on this fully packaged tag with the coil on the package and with a sensor interface, because it is a new development. Back then in 2014, we haven't seen this, so it's quite interesting to look at. It's called coil-on system, or not coil-on module, just because we have a full-fledged system on the device. We use, as I said, Infineon's EWLB packaging technology, embedded level bulk relay technology. And what you can see here is now a computer tomography of the device. And you can see here on top, we have an impedance sensor that is connected through these vertical interconnects here to this red biochip. That is a TMR, tunnel magnetoresistance sensor using CMOS. And this sensor interface and sensor chip are then connected through these vertical interconnects with an HF RFID tag, which is this, which follows the standard 14443. And this miniaturized coil that you can see that we designed to be embedded within the packaging. We had, in this case, the sensing device was devoted to detect magnetically marked biomolecules. It was created within a huge research project. We had many partners with different knowledge and also in the biomed industry. We then, our part in this case was we had to design the coil and the communication, make sure this is working out for the application that we intended. So here you can see now the realized coil. We designed it first using equivalent circuit models to see if we can be really successful in transferring power and communicating the information. And then we went back to a full wave simulator to take into account the packaging fan out area with its relative permittivity epsilon r of 4.1. And we designed the coil to match a chip of 56 picofarad. And in the end, we produced the chip and then showed it in the application and also showed what's the maximum read range we can get. So here you can see now the coil-on system tag, how it's now measured with respect how its read range is measured. You can see here the coaxial cable coming from the reader device, a little matching network to bring in the power, then a custom-built reader antenna, and we had 1 watt reader output power in this case, and we were able then to establish a communication range of about 1 centimeter, so 11 millimeter, which was okay for our point of care testing application. The size of the device was 6 times 4 millimeter, the height about 1 millimeter. Here you now can see the application that we wanted to demonstrate, point of care testing, detecting magnetically marked biomolecules. And you can see here the test strip for this point of care testing, where we would have here then the coil-on system. We put then the liquid with the magnetically marked biomolecules on top of it, and had here our reader device with its active area denoted here by this white sheet of paper. And we were able then to read out the sensor data successfully, and we're super proud of our development. But as I mentioned it before, so having these small devices reduces the read range considerably. But what you can do is you can use this booster antenna technology that I mentioned before. And so here you can see a video with a little tag where we had the coil-on chip and a so-called booster antenna. And we show here how the chip could be embedded possibly in human tissue. And we used a booster antenna just as a blaster on the human skin and then read out the sensor data. As you can see here, temperature of 19.2 degrees Celsius, of course, kind of room temperature. And so this is a possibility to then go towards other applications where you would need maybe more a higher read range, or where you deal with a severe environment for RF. And this is also what Infineon is doing with this coil-on module product. Booster antennas look actually like this. So if you have a coil on the chip, you have also here a small coupling coil at the booster antenna that has the same size as the coil on chip, and you bring them together. You align them so that you align this small coupling coil with the coil on the chip. And then connected to this small coupling coil, you can see you have a bigger pickup coil. And this could be the size again of a credit card to reach this 10 centimeter in read range. So 8 times 4 centimeter. And so by having now this booster antenna, what you can see is that you actually increase the read range because you have now a bigger area available at the transponder that can couple a magnetic field and can pick up the magnetic field. And usually Infineon is also using this in their coil-on module products. You can see here a video provided by Infineon with their coil-on module, the chip module here with the antenna. Here is the security chip that they use. And you can also see now the card, the payment card with the booster antenna, where you have here at the booster antenna this small pickup coupling coil, and then the larger pickup coil to help you gather more magnetic field and more power. Infineon actually, or card manufacturers, prefer using a coil-on module and a booster antenna because of reasons of costs. Because the galvanic connection that you need in a payment card from the coil to the chip is the most expensive thing of the whole payment card. And so if you can get rid of this galvanic connection, which you can do using the coil-on module and the booster antenna, there you have no galvanic connection, you have a reduced costs, but you also have a reduced mechanical robustness, because if a person uses the card and bends it too much, the galvanic connection between the chip and the coil can break. In this case, if you have a coil-on module and a booster, that their no galvanic connection can actually break. So that's another benefit of using this booster antenna technology. But as I said, I believe a month ago, I read in one of our newspapers that Infineon now has a new product available. It's based on a coil-on module realization, so coil-on package, but this time the chip, the radio frequency front end, as well as the coil are designed in a way that they're even more efficient and can harvest more power and establish then communication with the payment device. And so we have a larger read range here. So this standalone module that they created now, as you can see it here, provides a read range of about 4 centimeter, which is kind of okay for payment applications. And so they can get rid of this 2.8 meter size of coil that you would additionally have as a booster antenna if you use the coil-on module and the booster antenna. And so they get even more sustainable. And here you can see a realization that is completely out of a payment card, completely out of wood. So you just then, at the end of life of the card, you pop out the chip and the coil-on module here, and you can throw away this card, and you can even throw it, outside into the woods, because it's just wood and it will rot. So it's really good to see how RF design helps to establish sustainability. And I hope you had a good time listening to this talk. If you're interested, you can definitely contact me. I'll show you also my contact information below. Thank you so much.